Shuko, you know that I like driving, but I have to say, not like this.
I can totally agree with you. It is the worst.
When the rain gets so heavy that you basically can't see anything, I really wish that I already had a self-driving car.
Especially when it's now like in autumn, dark and cold, and, same with dense fog.
Clear vision is critically important when you're steering a vehicle. That's obvious.
Definitely.
But what if you have bad vision and the vehicle you're controlling is not on Earth?
Ooh. Doesn't make it easier, though, does it?
Not at all, but today's episode is about autonomous driving of a very special kind.
In a universe far, far away.
All right, not that far.
From know-how to wow. The Bosch Global Podcast.
This is the sound of a little rover. This recording is just from a test lab here at Bosch, but there are plans to put rovers like this on a rocket and send them to the moon. Over the past 3 years, it has been a task of a team of Bosch engineers to help make sure these little rovers can navigate the moon's surface.
I find this absolutely awesome. So, Geoff, how can we picture these rovers? Like RC cars or more like vacuum robots? Or are we talking clunkier and bigger like, Mars rover Curiosity?
Well, let me introduce you to Vivek from Bosch Research. He's the best person to answer all of your questions about this project.
My name is Vivek Jain, and I'm leading the wireless connectivity and sensing group at Bosch. We are looking at lunar rovers of the future to be a smaller design, so maybe like a shoebox or so. So maybe we can send multiple of them in the same lander, which could be utilized by different customers for different operations.
Okay, so thanks, Vivek. We're talking about a small swarm of shoebox-sized robots roaming the moon.
I don't know about that. What do we call a group of robots? Is it a swarm? In English, we have all names for different groups of creatures, like a colony of ants or a herd of cattle.
A pod of dolphins.
Or a flock of sheep.
I do like the word flock.
Yeah.
So a flock of shoebox-sized four-wheeled robots roaming the moon.
Sure. Why not? We should say right away, these robots are not being developed by Bosch. Mm-hmm. We are a partner in this project led by the company Astrobotic. Other partners include the startup Webotic, the University of Washington, and the American Space Agency, NASA. And to be even more specific, NASA's Glenn Research Center.
So if Vivek and his team are not building the robots, the hardware, they're providing the software.
Software to help solve one particular problem.
So one of the biggest questions is, how do we power these small rovers? Traditionally, when we design the rovers, we do put solar panels so that we can have the energy coming directly from the solar cells. Now, when we are talking about a very small design of a rover, the question is, where do we put solar panels?
I can see this as an issue because, the surface on top of the rover might not be large enough to generate the necessary power using solar panels.
Or if you put the necessary amount of panels on the rover, it could become unstable. So the idea is to put the panels on the lander instead.
Okay.
Which is a bigger piece of equipment and it's stationary.
We have solar panels there, of course, because there are a lot of electronics that is there on the lander that needs continuous operation and also connectivity back to the ground stations on Earth.
Yeah, that makes sense. The rovers could just go back to the lander when their battery runs low. Almost like those vacuum robots we have in our homes.
Almost, except...
This by itself is quite a complex problem.
Of course, everyone is going to realize that it's a little more complex on the moon compared to your living room.
What? Of course it is.
Of course. And the problem is there isn't as much it can use to navigate.
So I know that my vacuum robot uses radar sensors. And with their help, it detects obstacles and navigates around them. They also help identify, the walls and doors. But yeah, there are no walls or doors on the moon.
There isn't much for the radar signal to bounce off of. That's right. because radar needs reflections to work.
And we are talking about a flat moon surface. I mean, it can have craters and bumps there, but that is not good enough to give us an idea very precisely of where we are and use it for the navigation purposes.
And for this reason, the rovers don't have radar sensors built in for navigation. And of course, GPS won't do the trick either, as that technology relies on satellites.
Which obviously circle the Earth, not the moon.
Something that does work on the moon, of course, is vision.
One of the sensors that you will always find on the rover is the camera.
The primary use for the camera is actually not necessarily navigation, but rather science.
Because, of course, we need to look at the moon surface where we want to do the exploration.
But that's the rub. The camera is looking at the moon's surface.
Because the camera is not facing forward, the camera is actually facing downward.
I mean, at this point, Vivek should talk to the hardware guys, like, hey, could you make this camera maybe movable, move it down to do the science, and move it back up to drive back to the charger, right?
I like the way you think.
Move aside, Bosch engineers. I'm coming.
Well, that's a very good point. I mean, we can definitely discuss in the future designs of rovers. It could be an interesting point.
Maybe I'll become an aerospace engineer.
Shuko to the rescue.
Probably not in this life, but in the next one.
There is an argument against a movable camera, and that's that you want to keep the number of moving parts, of course, to a minimum.
Well, I did try.
Our current camera, it has a certain field of view. So it is about 86 degree horizontal and 70 degree vertical. But we are also angled the camera at a certain angle downward. So we only have about 5 degrees or so above the horizon that we can, see forward. The rest is all looking downward.
So going back to our driving in the rain scenario from the beginning of the show, maybe this is more like you have a fogged up windscreen and only been able to see a small sliver, a very small space to look through.
Not really great.
No, not at all. And to make matters worse, Vivek and his team have to consider the environmental conditions on the moon, which, again, of course, are not helpful to say the least.
The surface of the moon is very abrasive. So it has a lot of metallic particles as well. And with no atmosphere actually protecting the moon's surface, there is all the time the sun rays, all the radiations which are bombarding the moon's surface. And many times, it will also excite some of these metallic particles and they end up suspending into the air. We call it lunar dust. Now, on the Earth's surface, when there is a dust, because of gravity, it will come down fast too. We know Moon's gravity is much lower than Earth, so it remains suspended for a longer time. Now, these particles can also stick themselves to the camera, and if they stick to the camera, we may not have a very nice view.
Well, what do? When you have a lot of dust sticking to the windshield? I suggest spraying some water and activating the wipers.
Yeah, sure. Well, actually, it's not a bad idea. We did think about that too. But as lunar dust is quite sticky and abrasive, so if we use the wipers, we might end up actually scratching the camera lens surface.
So, Geoff, I think you and I will stick to what we're doing today because I guess neither of us are going to engineer a lunar rover anytime soon.
Thank you for the vote of confidence, Shuko, but sticky and or abrasive lunar dust is not going to stop me. At least it's not going to stop Vivek.
No.
Of course, we're not done with adding difficulty to Vivek's engineering problem, trying to make this rover find its charging port. Here's another environmental factor that makes it challenging. The moon doesn't have an atmosphere, or at least not the way I thought.
For a lot of years, we used to believe there is no atmosphere at all. It's only in the recent findings that we see, there is some light atmosphere, there's some sort of gases there. But in general, there is no dense atmosphere. So the surface, if the light is falling, is very, very bright. It can even go up to the light intensity of 130,000 lux. If I have to compare on Earth's surface, like in California, on a very bright sunny day, I may go up to maybe maximum of 80,000 lux. And here we are talking about 130,000 lux. So it's really, really bright light. On the other side, if there is a shadow, it's going to be really dark.
Meaning, you have extreme levels of contrast. The camera and its algorithms need to deal with that.
So that ideally the rover can see both what's in the shadows without them being too dark in the image, and what's in the sunlight without it being just all white and overexposed.
Yeah. So to summarize, it's really difficult for these robots to navigate by vision. It's dusty. It's either too bright or too dark. And they only have about 5 degrees of usable field of view vertically, but it's still the best information that's available to them. How does Vivek and his team compensate for the lack of clear vision there?
The way we have designed our solution for now is more like a sensor fusion.
That sounds so cool. Sensor fusion.
There are more sensors that can be used.
The camera is still the most important one, and its shortcomings can be mitigated by other sensors.
And that is where we all make use of odometry information. Like from the wheel, we can directly get some information about how fast it is moving or rotating. But since there are wheel slips, which are possible, so that information is also not totally accurate. So we also make use of IMU information. From the IMUs also, we can get our yaw angles and angular movements. And so as a supplementary information, we make use of that.
IMUs are inertial measurement units. In short, small sensors that detect movement.
So with those and the wheel speed sensors, there's pretty good information available about how the rover's moving. You can even detect when the wheels are slipping, thanks to the camera.
Do we see that we are moving 1 image to 2 image? If we don't see we are moving, maybe we are just rotating at the same place and doing nothing.
That's a great example. So clearly the algorithm takes in all the data from the different sensors and draw conclusions from that.
Okay, so now the rover kind of knows how fast it's moving and at what angle. At what angle in relation to what, though? Where does it want to go?
It wants to go to the charger.
Now, I understand the conceptual goal, but how does it know where the charger is? I mean, on the lander, but how does it know to find the lander? We talked about no GPS. We talked about limited field of vision. It doesn't know where the lander is or what it looks like. Turns out that's intentional.
Again, the point here was that we wanted the solution to be agnostic to lander. So the system could be used for any sort of lander from anybody. It doesn't have to be only Astrobotic, but it could be landers from other providers too. And that's the reason we don't want to use any of the lander features while designing our solution.
The solution is a visual marker.
So are we talking more on the lines of a QR code?
Actually, very similar. The team tested a few different solutions and eventually went with April tags, which are a very coarse QR code.
Okay.
So that gets deployed where the charger is. Once the rover sees those black and white pixels in its camera image, then it knows where to go. It works. Let's teleport ourselves to Vivek's lab, where his team tested this under various lighting conditions they could manage to create in the lab.
We got some floodlights. We got all these high-intensity lights that you use in the stadiums and all to generate that scenario in the building. But there are challenges as well. I mean, because many of these sources, they are very, very nice focus light you can have on the optical marker, but and all the ambience is so much contrast in terms of darkness and all, that we still get a very faded image. So creating the environment which is more realistic is already a big challenge.
So what if, and I don't want to be the party pooper here, but what if this test environment wasn't, good enough? What if this rover is on the moon and it can't find the visual marker in the camera image? Maybe, there's a shadow going across the marker, making it unreadable.
Asking the hard questions here, but of course...
That's me.
Yeah, absolutely. And you're right in doing so. It could also be, a hardware failure. Maybe the camera isn't working for some reason. Now what? Can the rover still find the charger? The answer is yes, because it's one more piece of information that the rover can utilize.
One of the most, interesting aspect is, of course, wireless. Now, I'm from the wireless group, so I will talk about the wireless too. So since we have wireless that we are using to communicate between the rover and the lander, we can also make use of wireless fingerprinting.
Have you heard of wireless fingerprinting before?
So it rings a bell, and I believe it can be used for indoor navigation, like at a shopping mall. Your phone can look at the different wireless signals and their strengths and determine where it is.
That's pretty much it. The catch is that you need to know which signal pattern corresponds to which point in space. So you need a map of the signals to compare the signal to which you're measuring.
Okay, I got it. So someone needs to create the map of wireless signals, and then I can use it to determine my location.
And that's something that also works on the moon, because there's actually going to be Wi-Fi on the moon.
But we're not talking about the same Wi-Fi technology that I'm using right now to talk to you, right?
No, exactly the same.
Okay.
At least in this project setup, the wireless connection between the lander and the rover is Wi-Fi. And that's how they talk to each other.
Fascinating.
Right? And with the added bonus that as long as it has a map, the rover can use the wireless signal to navigate. So one of the first things the rover is supposed to do after it comes out of the lander is building that map. It's used as a reference for later.
We have predefined certain maneuvers that the rover is going to do. For example, it will just, back up at different distances, maybe 10 centimeter, 20 centimeter, 50 centimeter, 1 meter, up to 2 meters. And at different points, it will record how the wireless signal is looking at. Then once it is back, it will rotate by, 5 degrees, 10 degrees, 20 degrees, and it will again repeat the same thing. So during this initial process, it actually creates a course map for itself. It just fingerprints the area that is predetermined for doing autonomous docking.
The rover goes in a radial pattern to assess the surroundings. So what is the rover exactly mapping here?
Let's imagine the case where the rover already has this map saved, this wireless fingerprint of the area, if you will. Mm-hmm. And now it comes back and it wants to find the charger, but it doesn't know exactly where it is in relation to the charger. Here's what's going on in this scenario between the transmitter on the lander and the receiver on the rover.
You get a direct signal from the transmitter to the receiver, but you also get signals which are reflected from the environment. On moon surface, because the surface has some metallic properties, we also see that there are going to be ground reflections apart from the direct path that we will get. So if we are only getting the direct path, then we can already know from the signal strength how far we are from the transmitter. But when we have these additional reflections and all, we also get channel state information. Interestingly, this channel state information that we get is different for different points. And that is what gives us an idea about, where we are in terms of not only how far we are, but also at what angle we are from the transmitter.
So at every point in this area, the signal differs because the reflections from the ground are different. And as the rover approaches the charger, it can compare the signal to the signal map it recorded earlier.
I think this deserves a little wow. We haven't had one in the show yet.
Wow.
As the rover moves closer to the charging port, Vivek has one more trick up his sleeve.
Like any Bosch engineer?
That's our deal here. You see, the charging is done wirelessly. Like you might charge your phone or a smartwatch using a charging pad. Mm-hmm. You don't have to actively plug in a cord.
And it's exactly the same technology they want to use on the moon?
All right, not exactly the same, but it's the same principle.
Okay.
This technology works at a larger distance compared to what we have, on your desk or nightstand or whatever. Mm-hmm. So that provides an additional information to the rover.
Once we are within 10 centimeter region of the wireless transmitter for the wireless charging, at that point, we can also use wireless charging quality indicators. Am I able to charge? What sort of voltage I am receiving or power I am receiving? Am I going in the right direction or not, where it increases gradually? And then I can also use that to position myself well.
Now that's smart.
And I'm sure Vivek is happy to hear that because the project is called Smart Docking Software. Ha. So according to you, they have accomplished their goal.
Definitely. Huge tick box. And what I find so compelling is that they repurpose a lot of the technology that is already on the rover anyways. So the camera that's used to examine the surface for science, they use a tiny sliver of it to identify visual markers. And the Wi-Fi signal that you mentioned, that's there for communication, they use it for wireless fingerprinting. And we just talked about it, the power coming from the charger, they use it for the perfect alignment.
When you put it like that, I have one more example of this. You want to hear it?
Of course I do.
This actually has nothing to do with navigation, but with repurposing existing technologies. You know, another challenge is that it gets really cold on the moon.
Mm-hmm.
Temperatures can come below 150 degrees C.
Oh, God.
That's minus 240 Fahrenheit.
Sounds always worse the American way.
And a lot of different hardware that we put there in terms of electronics, batteries and all, they stop working. They are not designed for those low temperatures.
So how can the rovers survive the lunar night? Which, by the way, is as long as 14 Earth days. One of the partners of the project thinks that wireless charging technology can help.
It is not 100% efficiency. Like it's not 100% power transfer. So what happened to the rest of the power? So that is being converted in all the heat. It is all lost as the ambient heat. But we thought, okay, this is something that we can also utilize to actually make this lunar rover survive during the nighttime.
So the charger doubles as a heater.
Pretty much. If there are multiple rovers, maybe they can move more closely together so that the heat gets transferred from one to the next.
Like penguins.
Like penguins. Yes.
I just have this really sweet image in my head from these little shoebox rovers.
It is. That's so
the flock.
sweet. The flock of penguin rovers on the moon huddling together for warmth. I just hope they don't waddle.
So with this cute image in mind, I still have one important question. When will these rovers with their smart docking softwares actually go to the moon?
Again, straight to the point. I love it. The development actually is pretty much done. Some final tests are still pending, but the project is basically finished. When the rovers will go to the moon, obviously that's not in Vivek's hands, but in the hands of NASA and Astrobotic.
We are really looking forward to when it actually goes into space. So we are waiting to see the first results, how nicely it worked with wireless charging and the navigation. I mean, we are eagerly, I will say, waiting for that, for those moments.
I would be so nervous.
Yeah, I can identify with that from being in the security space, but I would definitely have some sleepless nights if there was a moon mission resting on my software.
I think we have a lot of confidence in the software that we have, but we might still have a sleepless night before that the day it actually launches.
That's very relatable. But wow, what a ride. And as always, thank you, Geoff, and thank you, Vivek. Now we know how to navigate without GPS, with limited vision, and in super bright sunlight.
Try to make use of that next time you have a foggy windscreen.
Just don't drive with a foggy windscreen.
Nope, don't do it. Well, maybe one day when and if some of this lunar rover technology makes it back to the cars on Earth.
Mm-hmm.
But anyway, thanks for listening, everyone. We'll be back next month with a brand new episode for you. Hear you all soon.
Au revoir.
From know-how to wow.
Guys, I am so excited for next month's episode because I'll get the chance to test drive Bosch's latest motorcycle technology. So maybe for our new listeners, I'm a huge motorcycle fanatic and I'm going to go test some assistance systems like you've never seen before. And I cannot wait to tell you all about it. So stay tuned and see you next time.
I'm not jealous at all.
Woo! I know you're not. You like your cage. You're a cager.
I am a cager. That's... I've never been called that before.
The Bosch Global Podcast.